name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on organic reactions, carbonyl compounds and functional groups. And this is for the colour by design topic, or CD topic for OCRB salters. So this video is designed to go through all of the points for the salter specification and the CD topic. This is one of 3 videos for the CD topic, so I've split it up into 3 parts just to make it a little bit easier to kind of navigate your way through this quite large topic. So this one's mainly going to look at these parts, like I say. I've also done a full range. These are revision videos. Anything with a black screen are revision videos. So I've done a full range of videos for salters for year 1 and year 2 chemistry. And also I've got some generic whiteboard tutorials as well, which go through specific areas of chemistry. So if you wanted to know about titrations, for example, you can go and look for it there. So there's loads of stuff on Allery Chemistry. It's all for free, so all I ask is you hit the subscribe button. That'll be absolutely fantastic, and as long as people keep subscribing, liking and watching the videos, then I will keep on making them, and I'll update them when new specifications come in as well, and expand the channel as much as I can to cover as many different things. Also, this video is made from revision slides that I've made. They are available to purchase in the link in the description box below. They're great value for money. You can use them on the move, smartphone, tablets. I've known people to print them off as well and use them as revision notes in their files. So go and have a look on there. They're really, really good value for money. You get the full range as well, year 1 and year 2. Okay, so like I say, this is dedicated to the salters specification, as you can see there, and this video is going to talk through the following points. So we're going to be looking at functional groups. I'm looking at the different types of functional groups, and we're going to be looking at some of the ways in which we can test some of them. So you would have seen a lot of them throughout salters chemistry, but towards the end of the video, we're going to look at just a specific example, just so you know what we're talking about. We're then going to look at some organic reactions as well, using aldehydes and ketones. We're going to be looking at carboxylic acids as well, and how we actually make them using reflux and distillation, as well as chemical tests for them as well, such as Fehling's and Tollens reagents. And we're going to look at some reaction mechanisms as well, looking at the addition of cyanide ions, for example, to aldehydes, and look at some of the mechanisms and classifying organic reactions as either addition, condensation, elimination, substitution, oxidation, reduction, and hydrolysis. And we're going to look at a bit of nomenclature as well. So there's quite a bit in this video, as you can see. Okay, so we're going to start by looking at aldehydes and ketones first. So aldehydes and ketones have the carbonyl functional group. That's the C double bond O group. That's what they all have. And so the difference between aldehyde and ketone is quite simply the position of that carbonyl group. So we'll start with the aldehydes first. So aldehydes have that carbonyl group on a terminal carbon. Okay, so it's not midway through the carbon chain. These are always at the end, and we call them al. We have al at the end, so aldehyde. Okay, so for example, methanol, methanol, butanol, propanol, hexanol, etc. So you just add al on the end. So let's have a look at an example. So this one is propanol. Okay, so you can see here that we've got 3 carbons, so it's prop, and you can see we've got this carbonyl group on the end carbon there. So this is why this one's called propanol. This one's called ethanol because we've got 2 carbons, as you can see on the end there. So fairly straightforward for aldehydes. So ketones are very similar to aldehydes, except that carbonyl group is in one of the mid carbons, so it's halfway through the chain, or it's not an end carbon. So a carbonyl group that isn't on the end is a ketone. So you can see here we have an inner carbonyl group, and we end that on -one. So for example, propanone as an example. Okay, the differences with this is actually the nomenclature of ketones is a little bit more complicated, because you've got to also specify where that carbonyl group is. If you've got carbon chains of, let's say, 4 or more, you've got to state where that 5 or more, you've got to state where that carbon chain is. So let's have a look. Here's an example. This one's called propanone. Obviously, there's only one position that this carbonyl can take, and that's the second carbon there in the middle. Okay, and also you can see here that we've got one with 5 carbons in here, so we've got to specify exactly where that carbonyl group is. On this case, it's sitting on the second carbon because you've got 1, 2, 3, 4, 5 carbons in a chain. So this is sitting on carbon 2, so we call this pentan 2-one. Okay, so just be aware that you do have to specify where this carbonyl group is if it's a ketone that has got a longer carbon chain, as you can see there. Okay, so we're now going to look at, obviously we looked at aldehydes and ketones. We're going to see about how we can actually make aldehydes and ketones. And we actually make them by the oxidation of alcohols. And we're going to need to know about the practical techniques as well associated with this. So alcohols can be oxidized to aldehydes, ketones, and to carboxylic acids. So alcohols are oxidized using acidified potassium dichromate, so K2Cr2O7. It's a mild oxidizing agent, so is reduced itself. Okay, so remember that. So you would have seen that in a previous video, particularly the one where we're looking at redox, the electrochemical cell. So that's redox in the DM topic, I believe. So that video we talk about redox in a lot more detail, and we talk about what an oxidizing agent is. So remember, oxidation is the loss of electrons, reduction is the gain, but an oxidizing agent gains electrons, okay, and a reducing agent loses electrons. So it's the opposite effectively. So this is a mild oxidizing agent, so it's reduced itself, like I say. It will turn from orange, which is your dichromate ion here, Cr2O72-, and it will go to a green chromium 3+ ion. Okay, so that's a classic sign that this reaction has actually taken place. It's an indication, and we'll look at that towards the end of the video as well when we're looking for testing for functional groups. Okay, so primary alcohols, these can be oxidized to aldehydes and then onto carboxylic acids. So the first step is taking your alcohol and converting it to an aldehyde first. So remember, your aldehyde has the carbonyl group at the end here, as you can see. So this one, in this case, is propanal, because we've got 3 carbons there, and we've got ends in al, okay, with it being an aldehyde. And this can be oxidized further to a carboxylic acid. So in this case, this is propanoic acid. So carboxylic acids have this carbonyl group here, and they have an OH group attached to that too. Okay, so this is called a carboxylic acid. So primary alcohols can be oxidized to an aldehyde, then to a carboxylic acid. Secondary alcohols, these can be oxidized to ketones. So ketones, as we've seen before, there's a ketone there. They end in -one, so this one is propanone. Okay, so secondary alcohols are oxidized to that. There is no further oxidation though, so primary alcohols can be oxidized to aldehydes, then carboxylic acids. Secondaries can be oxidized to ketones, but nothing else. That's the only step that it can go to. And then tertiary alcohols, they can't be oxidized at all. So they can't be oxidized using dichromate, using these reagents that we're talking about. Only through burning them can we oxidize them, but then we actually destroy the integrity of the molecule. So tertiaries, in other words, don't oxidize. So you need to know primaries oxidize to aldehydes and carboxylic acids, and secondaries oxidize to ketones, and tertiary alcohols don't oxidize. As long as you know that, that's the main thing. Okay, so distillation and reflux is the method in which we use to actually make these products that we've just seen there before. So for primary alcohols, these are oxidized, but the products produced are dependent upon the method that we follow. And we actually represent an oxidizing agent using O in a square brackets, and you'll see that later on. Okay, so we have to be really careful, particularly with primary alcohols, if we want to produce an aldehyde, because we've just seen before there, aldehydes readily oxidize to carboxylic acids. So we've got to make sure that if we do want to make an aldehyde, that we use the correct equipment, the correct method. So let's have a look. Okay, so your oxidizing your primary alcohols produces an aldehyde, then a carboxylic acid, but it's really difficult to just extract your aldehyde when we're just heating it in a boiling tube. Okay, so we don't just use a boiling tube to actually react this. What we must do is we must remove this product first. before this oxidizes to carboxylic acid. So we've got to use a bit of kit that allows us to separate this out. As soon as it's formed, separate it, get it into a separate container, because if this then drops back down into the reaction vessel and is allowed to react with an oxidizing agent, then you'll just form your carboxylic acid. So at this point, we use distillation kit. Okay, so the distillation is used to separate your aldehyde as soon as it's made. And this is because your aldehyde is a lower boiling point than the alcohol. So this can be evaporated off at a lower temperature, so that can then be condensed into a separate container. Now, like I say, if we didn't do that, and we just continue to heat it under reflux, which is this here, then effectively this will oxidize further to a carboxylic acid. So if we wanted to make a carboxylic acid, then we can use a reflux setup here, like so. So we heat up our reactants. Obviously, some of our compounds would rise up. So for example, aldehyde would start and rise up, hit the condenser, cool, and drop back down into your reaction vessel, where it will react with more oxidizing agent, and then that will produce your carboxylic acid in this reaction vessel here. So reflux is ideal if you're making a carboxylic acid. It's not great if you want to make an aldehyde. You have to use distillation instead. Okay, so reflux allows us to heat something strongly, and it's ideal when we're heating volatile compounds together. What we don't want to do when we're heating any types of these chemicals, particularly organic chemicals like this, is actually they're quite volatile and they readily escape from the reaction vessel. So using a reflux setup allows us to heat our chemicals up, allow them to react, but we're not losing the product out to the surroundings, because they hit against this condenser, cool, condense back down, and fall back down to the reaction vessel. So it's a way of containing our reactants and products in one vessel. Okay, so for secondary alcohols, these are oxidized to ketones. It's really difficult to oxidize ketones further, so we assume that they don't. And we represent an oxidizing agent using O in a square bracket. So you can see here that we've got our secondary alcohol. There it is there. Okay, now for this one, we don't need to bother using distillation because there's only one step. We oxidize it to a ketone. So we just use a reflux setup, as we'd seen for making a carboxylic acid. We use a reflux. So we just heat that up and just produce our ketone. So there's our ketone there. Excuse me. Okay, so your secondary alcohol will produce, so this is propan-2-ol, will produce propanone, and this is used when acidified potassium dichromate is used, exactly the same oxidizing agent as what we'd seen before. Okay, so we know kind of what we've produced here. So we know how to make an aldehyde, what method we need to do, we know how to make a carboxylic acid, and we know how to make a ketone as well, okay, from a secondary alcohol, and we know the method for that. What we've got to be able to do is we've got to be able to test to see if indeed we have produced an aldehyde or a ketone. Okay, so chemical test is really important because all these chemicals are colorless liquids, and it's really difficult to distinguish between the two without any form of test. So this is what you need to know. You need to know about the tests for aldehydes and ketones and some of the reactions as well for them. So Fehling's or Benedict solution can be used to distinguish between aldehydes and ketones. So Fehling's and Benedict's, these are oxidizing agents in their own right. So they act in a similar way to, they react in a similar way to your potassium dichromate that we'd seen before. So what they will do is they will oxidize aldehydes, but remember, ketones can't be oxidized any further. So actually by using either Fehling's or Benedict's, we can actually test, because they'll show a color change, or that you'll see a change, and that will help us to identify if we do have an aldehyde, because aldehydes can be oxidized, or if we have a ketone, but they can't be, so you shouldn't see any change reacting with the ketone. So let's have a look at Fehling's first. Okay, so Fehling's and Benedict's first. So Fehling's and Benedict's solution is blue. It contains copper 2+ ion, so it's like copper sulfate solution, as you can see here. Okay, and then we add it warm to aldehyde, so we put it into a hot water bath, and if we add it to an aldehyde, then we should get a blue solution, and we should get a brick red precipitate that's actually formed here. Now with ketones, they just remain blue, because remember, ketones can't be oxidized any further. Your aldehydes can be oxidized, so therefore you get this color change, as you can see. Now, Phalings, the main difference between Phalings and Benedicts is Phalings, the copper ions are dissolved in sodium hydroxide, or the copper 2 plus ions are dissolved in sodium hydroxide solution, and Benedict's is the same ion, still blue, but it's dissolved in sodium carbonate. So that's the only difference that you need to know. But the test is the same. The outcome of the test is the same. So the reaction, you need to know the reaction for this. So we're going to show you the full reaction. This is your half equation. So you can see here we're going from an aldehyde. We've got a copper 2 plus. The copper 2 plus is turns to Cu2O, as you can see there. So this is copper 1 plus. So you can see the copper has been reduced here. We're using hydroxide ions as well, and you can see that we've reduced our, we've oxidized our aldehyde to our carboxylic acid or carboxylate ion, as you can see there. And effectively, we can simplify this to Cu2 plus, picking up that electron to form Cu plus. So you can see this is clearly being reduced because the oxidation number has gone from +2 to +1. So this has been reduced, but in return, the aldehyde has been oxidized to your carboxylic acid, as you can see there. Okay, so another way of testing for aldehydes and ketones, because there's never just enough just to have one, is there? Well, this one's probably the best one, I think, is Tollens reagent. And this can be used to distinguish between aldehydes and ketones also. Now, Tollens reagent uses a silver complex, basically, but we have to make that silver complex first. So we need to know how to make Tollens reagent, and then once we've made the reagent, we can then add an aldehyde and a ketone in there to... or we add our unknown chemical to distinguish if it is indeed an aldehyde or a ketone that we've actually made. So the first step in making it is we need silver nitrate solution. Now that is colourless, and that goes into your test tube, as you can see there. And then what we do is we add a few drops of sodium hydroxide to it, and we get a pale brown precipitate that forms on the back of that, as you can see there. Then once that's done, then what we need to do is, you can see we need to add a few drops of dilute ammonia until that precipitate starts to dissolve. And actually our outcome is that we've made Tollens reagent. And it's this reagent that we then use to distinguish between your aldehyde and ketone. So what we do is we add our aldehyde and ketone in there. We use a water bath as well, a hot water bath. It just allows the reaction to go at a timely fashion. And we don't use a Bunsen burner. We never do with any of these reactions. That's an important point, actually, even with the Phalings and Benedict solution that we'd seen before. We mustn't use that because the chemicals we use, organic chemicals, are flammable. So we shouldn't be using any of them, otherwise you'll have a bit of a problem on your hand. So what do we see? Well, the Tollens, it contains this silver complex, like I said here. Okay, so that's a complex there. So remember from the DM topic, you'll know what a complex is. So this is your silver complex here. When it's added to aldehydes, we get a silver precipitate. It's really nice. If you've done this in school or college, you'll know what I mean. It literally, you get silver that's lining the side of your test tube. It coats it. It's really, really nice. With ketones, it's not so fun. You don't get anything. Because remember, ketones can't be oxidized. Aldehydes can. Your Tollens is effectively an oxidizing agent, so it will oxidize aldehydes but not ketones. So we get this silver mirror. It's also known as a silver mirror test. So we get this silver mirror that appears with Tollens reagent. So we need to know the reaction involved with this as well. So Tollens is made using silver nitrate with aqueous ammonia. So remember, that's what we'd said before. And when reacted with an aldehyde, it reacts in the following way. So you can see here, there's our silver complex there, reacting it with our aldehyde, and it's got to be in an alkaline condition. Okay, so this is with aqueous ammonia, remember? So alkaline condition, and it reduces, so your silver here is reduced, so it goes from Ag plus, as you can see there, to Ag, so that's going to an oxidation state of 0, so it's gone from +1 to 0, so that's reduction. So that's your silver solid, that's your precipitate that lines the test tube. You've got your carboxylate ion, as you can see there, 4 lots of ammonia and water as well. So actually you get this sense of this smell of ammonia coming from it as well. And it can be simplified to this. This is your half equation. So you can see you've got AgNH3 Okay, so these two ammonias, ligands, these are the ligands, they break off. Obviously that forms it there. You've got silver okay, silver solid, and obviously that picks up an electron. So this is showing a reduction process, forming that silver precipitate on the side there. Okay, so that's fine. So we know how to make aldehydes and ketones and carboxylic acids. We know how to test for aldehydes and ketones using Fehling's and Benedict's and Tollens reagent. Now what we have to do is understand about their reactions. So we're now going to be looking at hydrogen cyanide and the reaction with the carbonyl group, which exists in aldehydes and ketones. So hydrogen cyanide reacts with carbonyl compounds to form something called cyanohydrins. Okay, so the reaction occurs via nucleophilic addition mechanism. Okay, and it means a nucleophile, that's your CN- ion, this attacks the carbonyl group, that's that C double bond O, and it adds on to make cyanohydrin. Okay, and a cyanohydrin, as it kind of explains, contains a cyanide group, which is CN, okay, and hydrin, which is your hydroxyl group, which is here, which is OH, okay. So hydrogen cyanide is used to produce the CN- ion, so that's what we need to attack a carbonyl group. And so when we dissolve this in solution, we actually form an acidic solution as well, and we need the H+ ions for this reaction to go. So it's really handy chemical to use. So you've got hydrogen cyanide. When it's dissolved in solution, it breaks apart to form the cyanide ion that we need to allow the reaction to go, and obviously H+ ions make the solution acidic as well. So let's have a look at the mechanism. So here we've got an aldehyde here. So our aldehyde has got a delta positive carbon, a delta negative oxygen, as you can see on there. There's our cyanide ion. Okay, so this is our nucleophile. So remember, nucleophile is nucleus loving. So these species have a lone pair of electrons, and they will go and attack this delta positive carbon, as you can see there. Okay, so this is your nucleophile. So that's exactly what it does. So the positively charged carbon atom in that carbonyl group is attacked by the cyanide ion. The lone pair of electrons are donated from the CN- ion, and that's what makes it that nucleophile. So this goes in and tries to bond with that carbon. Now you can see here that we're forming a bond here. That's 1, 2, 3, 4, 5. We've now have 5 bonds around that carbon. One of these bonds has got to break, and that's going to be coming from the double bond there. So let's do that. There it is, okay? So the 2 electrons from the double bond, they transfer to the oxygen. Okay, really, really important. Okay, so that's your first step. So we're not there yet. We've just halfway through this mechanism. Okay, so we're going to see this on the next slide. So the hydrogen cyanide, you've got to be really careful. It's highly toxic and must be handled with care. It must be handled in a fume cupboard because it's not very nice. You don't want to breathe this stuff in. So you might not have actually done this reaction yourself. Your teacher or lecturer might have done it instead. Okay, so just carrying on with this mechanism. So we form this intermediate there with the O-. Now the lone pair of electrons on that then react with the H+ ion. So remember that H+ ion supply is coming from the hydrogen cyanide that we used initially. So remember when we dissolved that in solution, the H+ ion, and we formed the CN- ion. The CN- ion was used before. Obviously you can see it added on there. There it is. And the H+ ion is then used to protonate your oxygen here. Okay, and then that forms our final product, our cyanohydrin. And so it can also be called a hydroxynitrile as well. You might see 2 words or both words being used, but for salters they prefer you to use cyanohydrin instead. But just beware if you're reading other literature, let's say online or in your book, and you see hydroxynitrile, it's the same thing. Okay, so this is cyanohydrin, which is there. Okay, right. So let's look at, so we've looked at, obviously we looked at some of the reactions. We need to know the mechanism for this. It's good marks. Make sure you're being really specific with your arrows. Remember, mechanism arrows show the direction of electron travel. So it's going from somewhere with electrons to somewhere with very little electrons. Okay, just make sure you're being able to write these and draw these mechanisms properly. You get a lot of marks for them. Right, so now we're going to move on to kind of summarizing some of these ideas here, and we're going to be looking at some functional groups and the nomenclature of it. So all the way through the course, year 1 and year 2, you've come across a multitude of different organic compounds, different functional groups, and loads of different reactions. And really, this part here is about pulling all of that together and being able to apply it to nomenclature and also testing. So the rest of this is really going to be looking at summarizing these parts and pulling it all together. Really important, because there's going to be a lot of interlinking in the exam, and this could be quite tricky for you. So, okay, so when we're naming compounds, okay, organic compounds, there's an order of priority of how we name them and how they should be classified. And we're going to look at the order here. Now, you don't need to worry too much about you don't need to worry about exactly about the remembering every single one of these. You'll get used to naming compounds just through experience and through naming. You would have named hundreds and hundreds of compounds, throughout A-level chemistry. But this is just a formal thing. This might be a good idea, actually, for you to maybe print this out, and pin it to your wall or something. And then when you're naming it, you'll kind of get used to, learning how to name it. So just to kind of give you a brief walkthrough, I'm not going to dwell on this too much, because like I say, we're going to see the use of this table in the next slide a lot more. So you've got carboxylic acids and diols. These take priority, and depending on, you can either call them carboxy or oic acid, and dicarboxy or dioic acid if it's a diol. So this takes priority. So if you have one of these in your molecule, and we're going to look at polyfunctional molecules as well, but polyfunctional group molecules, then this would take priority in terms of your naming. Anhydrides then follow. They only have a suffix of oic anhydride. There's no prefix option with these. And then it goes down, all the way down here. So esters, acyl chlorides, amides, aldehydes, ketones, alcohols, diols, phenols are at the back here. Okay, so they always end in phenol. Okay. Primary amines and diamines, as you can see there. Alkenes always end in ene. Arenes can either be phenyl or benzene at the end there. Okay. Alkanes can be ane. Ethers are alkoxy, and haloalkanes, these always have a prefix. These are the lowest priority. So when you're naming it, you have to decide what's a functional group and what's your core molecule. The higher the priority, the more likely it's going to be, your core molecule, and anything coming off that is going to be named accordingly. But I think the best thing is when we're looking at polyfunctional groups or polyfunctional molecules, I think the key thing is being able to identify which takes priority and how do we name it. So the best thing, like I say, print this off. You can get a copy of this in the link below. Great value for money. Get a hold of this, get it printed off, and then you'll be able to name as many molecules as you want, and you should be fine. Easy marks in the exam, but you need to know your priorities. Okay, so let's have a look at some examples here. So when naming compounds, there is an order of priority of how you name them and how they should be classified. Okay, so let's say, for example, you have a molecule with a carboxylic acid in and a ketone, and you look at the table that was shown previously, so you have that in front of you. Okay, the functional group with the highest priority will be the one which gives its suffix to the name of the molecule. Okay, so remember, a suffix is the bit at the end, a prefix is the bit at the start. So for example, the prefix might be chloro something, bromo something. A suffix would be oic acid, for example, like a carboxylic acid. So as a carboxylic acid is number 1 in the list, the suffix of the molecule will be oic acid, not on, because carboxylic acids are given higher priority. Okay, so in what we're saying is, with the carboxylic acid, you have a carbonyl group and you have an alcohol group. So you've got to use oic acid at the end. Okay, so it's got to be that one. So however, if a ketone is present with an alcohol, okay, so this is to do with a carboxylic acid and a ketone. So that's why we're saying, because a carboxylic acid is higher in priority than a ketone, then we name it oic acid and not on at the end, if you see what I mean. Okay. So however, if a ketone is present with an alcohol, okay, we use the suffix on, because ketones have a higher priority than alcohols. So it's all about, which is higher up in that pecking order, and whichever's higher up, we use the suffix of that to kind of start us off. So let's look at some 3 examples here of polyfunctional molecules. So let's see if you can have a go at this. If you've got the table in front of you, that's fine. If not, pause it, go and have a look, and see if you can classify what this reaction is. Okay, so this one is going to be either an alcohol or carboxylic acid. Well, this one's going to be a carboxylic acid, of course. Carboxylic acid has a higher priority, so we name this according to a carboxylic acid. So you can see I've got 1, 2, 3, 4, so it's a hydroxy group on the end of the fourth carbon of a carboxylic acid. So the carboxylic acid is the priority here, okay? So what about this one here? Is this a phenol or is this a carboxylic acid? Okay, well this one is also a carboxylic acid, of course it is. So we know it's a carboxylic acid because that takes priority over a phenol. So you look at this here, and obviously this is going to be phenyl, okay, a phenyl acid group. Okay, so this is your carboxylic acid here. Okay, so that takes priority. Okay, and what about this one? Is this an alcohol or an alkene? Excuse me. Okay, which one takes priority? Well, the priority one in this case is going to be an alcohol. So we name this as an alcohol, so it must end in "ol," okay, because that's the highest priority. So we give the suffix of this compound "ol," or in this case it's diol because we've got two alcohol groups either side. So I hope you've kind of got the idea of that. It's about trying to find out, what is this chemical? What's the root of the chemical? And then whatever else is in there are just branches, they're subgroups, so to speak. So it's about trying to identify that. Okay, so you need to be able to name compounds using them priority rules, as we've seen before. Okay, so obviously with them molecules, it's about identifying the core of the molecule. But now we have to be able to name them using them rules. So let's have a look using them rules, them classified rules before. So this one here. So again, see if you can try and name it. Pause the video and see if you can try and name this molecule. Bearing in mind, find out what the priority group is, the core of the molecule, and then name the other parts. So this one, you can see that is your priority. That's your carboxylic acid and your hydroxy, and that's 4-hydroxybutanoic acid. So that was the naming of that first one. Okay, because we know it was a carboxylic acid, so it must end in oic acid. Okay, what about that second one that we'd seen before? So again, pause the video, see if you can name it. We know what the priority group is in this. This is the carboxylic acid. Okay, so this one's going to be that. There's your priority carboxylic acid. And we have our hydroxy group, as you can see in the bottom there. So this is 2-hydroxy benzoic acid. Okay, so benzoic acid is the priority. That's the carboxylic acid, and you've got a hydroxy coming off the second one. Okay, so it's not a phenol. Right, and then the last one, this one here. So pause the video, see if you can work it out. Okay, well the priority group in this was the alcohol, but there's 2 alcohols, so this is going to be a diol. There we are. Okay, and then we've got our alkene group in the middle, so this is going to be but-2-ene-1,4-diol. So it must end in ol because alcohol was the priority group. Okay, so I hope that kind of makes sense. I think the key thing is just knowing the priority, the orders of these. Okay, but you'll see these a lot. You'll write this a lot in throughout chemistry. So you may be familiar with some of them anyway. So it might be the case that you know half of them anyway. But it's always a good idea. Print that off and then you've got a record of it. Okay, right. So we need to run multiple chemical tests to identify functional groups in polyfunctional molecules. Okay, so we need to be able to identify them. So we need to know individual chemical tests for functional groups to help us confirm or eliminate certain functional groups and prove a polyfunctional molecule. Okay, so polyfunctional molecule is where you've got more than one functional group in there. So let's have a look at this one. So here's an example. This is salicylic acid, which is used to make aspirin. So salicylic acid is used to make aspirin, but also directly it's used to treat verrucas and warts. And it has this following formula. So you can see here it's got a couple of functional groups in there, that one that we'd seen before. And so if we add the following chemicals separately, what will we observe and what can we deduce? So this might be an example in the exam that they'll say, right, here's a chemical here, and they'll give you something a little bit obscure that you might not have seen before, and they'll basically want you to deduce or rule out or include certain aspects of this chemical based on chemical tests. And this is why chemical tests are so important. We're going to be reviewing some of them, not all of them, but some of them towards the end of the video. But they're really important because it allows us to identify certain chemicals. So we're going to add sodium carbonate solution, We're going to add acidified potassium dichromate under reflux, and we're going to add Tollens reagent as well. So we need to go, what the examiners are wanting us to do here is to go through each one of them and tell us separately what we will observe and what can we deduce from that observation. So if we add sodium carbonate solution to this particular chemical here, we will see fizzing. Now why? Because it's an acid. So remember, one of the tests, and we'll see it towards the end of the video as well, one of the tests of an acid, like a carboxylic acid in this case, is you add it to a carbonate and you see fizzing. So this is a sign of a carboxyl group because this is an organic compound. So that tells us that we must have an acid group in there. So what about the addition of acidified potassium dichromate under reflux? Well, we will see a colour change of orange to green because we have an alcohol group in there. There's our alcohol. And this is oxidized to a ketone. Okay, so in this case, yes, this will be oxidized further. And so therefore, we will see a colour change of orange to green. Okay. And then the third one, we see no visible change when we add Tollens reagents. So this is telling us that there isn't an aldehyde group in our compound here. We don't have an aldehyde. So you can see here what we're trying to do is rule in or rule out certain chemicals, and you need to understand what chemicals we can use to test for them. Okay, so we can also use melting points as well to determine if we do have polyfunctional molecules, or do we just have a mixture of different substances? In other words, do we just have a mixture of alcohols and carboxylic acids and halogenoalkanes, etc.? Do we just have a mixture, or do we truly have a molecule, the one molecule with different functional groups attached to it? And so melting point apparatus can help us do this. So the chemical tests that we've seen before, they do not necessarily mean that we do have a polyfunctional molecule, because we have an impure sample that may contain all of them, just a combination of 3 of them different chemicals in there. So it's not definitive proof that it is indeed a polyfunctional molecule. So we can actually get around this by using a melting point apparatus, and we can test our solid by putting it into an apparatus like this. Now before we do that, we actually use a very fine tube, a capillary tube, which we tap gently like this, okay, against our powder, and the powder starts to migrate its way up the capillary tube, and it's just a really, really thin glass tube. And then what we do is we place the capillary tube into one of these little entrances at the top here. So we take the cap off, we put it into the top there, and then we view down the middle here. And basically this machine's got a little oven in it, and what it does is it warms it up gently. You can control the temperature using these controls here, and you can see the solid magnified down this viewfinder here. And what we're looking for is we're looking for that solid to melt. Now if we have a pure polyfunctional molecule, we should get a really sharp melting point, so it all melts in a very narrow range, and we can control the temperature. This is heavily controlled temperature, we can control that. Impurities, if we had a mixture of different molecules and it wasn't polyfunctional, then what we would see is a melting point range that's much broader. Okay, so we've just got to be looking for this. So we do our chemical tests before, fine. We then put it through a melting point apparatus like this. And if we do get a sharp melting point, we can be confident that we do have polyfunctional molecules in there, and not just a mixture of different molecules with different functional groups. Okay, right, so now what we're going to do, we've kind of looked at a lot of that. We're now going to have to look at some reaction types, as we mentioned towards the start of the video. And there's 7 different reaction types that you need to be aware of, okay? And then what we're going to do after we've looked at this, we're then going to look at some of the, just a small sample of some chemical tests that are related to this video, but you need to know, you should know some of these already anyway. But let's look at these 7 groups first of all. So the first group are addition reactions. So addition reactions are akin to molecules with a double bond in there. So you can add chemicals to it. So these are things like, for example, you've got aldehydes here, you've got ketones, and we've got alkenes as well, so we can add to that double bond. So they've all got this feature, and we'll look at the tests. We'll look at the tests for these chemicals, all three of these, later on. So using bromine, for example, using Tollens or Fehling's or Benedict solution for this one, and this one as well, which is your aldehyde. Okay. So addition reactions, the bond's broken and we add a chemical to that. So the second one is substitution. So a functional group is exchanged for another one. So classic reactions involved in substitutions are halogenoalkanes or halide molecules, phenyl or benzene compounds where the hydrogen is substituted. So you would have seen that with within this topic, in fact, about the nitration of benzene, sulfonation of benzene, Friedel-Crafts alkylation and acylation. So we've got a lot of reactions there. And then we've got alcohols as well, so we can substitute alcohols. Okay, so elimination and dehydration is the third way. So a double bond is normally formed when a functional group is removed and released as part of a smaller molecule. The functional groups involved with these ones, because it's elimination or dehydration, then are halogens and OH minuses, so it can form hydrogen halides are eliminated, or water, which is a bit more obvious with dehydration. So dehydration reactions is when water has been eliminated. So these are the types of reactions there. Okay, so the fourth type of reaction that we need to know are condensation reactions. So this is when two molecules join and a small molecule is eliminated, such as water is a classic example. So the functional groups involved are normally things like acid chlorides or acyl chlorides, carboxylic acids, amides, hydroxy groups, so alcohols, for example. So these are all involved in condensation reactions, and are involved in things like polymerization, for example, your fats and oils that you will have seen. So they are all examples of condensation reactions. So water has been eliminated. Another one is hydrolysis. So hydrolysis meaning hydro meaning water, lysis meaning to break. So we're splitting molecules up using water. So classic examples here are, for example, the breaking of polyamides and polyesters. So the breakdown of your polymers. This is done through hydrolysis, or you can do ester hydrolysis as well. So the breaking down of esters into carboxylic acids and alcohols. Okay, and the final type are oxidation reactions. So normally means gaining an oxygen or the loss of hydrogen. Sorry, it's not the final one. There's one more after this. This is number 6. I'm getting ahead of myself. So normally means the gaining of oxygen or the loss of a hydrogen in reactions. But theoretically, it's the one that you really do need to be commenting on here is the loss of electrons. So oxidation is the loss of electrons. So oxidation reactions, as we've seen, are alcohols oxidized to an aldehyde and a carboxylic acid, or secondary alcohol going to a ketone. Obviously, we've just seen that just before. And the final type of reaction is reduction. And reduction normally means the loss of oxygen or the gain of hydrogen, but in theory, you really do need to be talking about electrons. So reduction is the gain of electrons. Okay, so this is basically the opposite of oxidation. So we're starting with a carboxylic acid, as you can see here. This has been reduced to an aldehyde, then to a primary alcohol, and then a ketone being reduced to a secondary alcohol, which is the one on the right there. Okay, so you need to know all of these different reaction types, and as you can see, we categorize them into them 7 broad groups. But what we do need to know, and this is the final bit, is about the different tests of these functional groups. Now, you would have seen this littered all across Year 1 and Year 2 chemistry. What I'm going to do is focus on some specific examples just to give you a flavour, and in particular focus on some of the ones, 2 of them in particular, are some of the reactions that we've seen in this video. So let's just have a look at the first one, which you will have seen, just as a reminder really, for a test for alkenes, remember, is we react that with bromine water. Okay, so, and very simply, all we do is we add bromine water to an alkene. So your alkenes have that double bond. We then shake that test tube, so we give it a good shake, and if an alkene is present, then we get a colourless solution is formed. And this is an addition reaction, remember, because we're adding Br2 to an alkene and we form a dibromoalkane. is actually formed. So this is a classic sign of an alkene when we shake that with a double bond. Remember, this doesn't work with benzyl compounds or benzene because they don't react in the same way. They don't undergo addition reactions. They undergo substitution reactions, as you've seen before. Okay, so just back onto the theme of this topic, another test for a carboxylic acid. Obviously, we've seen how that's actually produced. You might have seen this before as well previously, so it's just a bit of a reminder. But we test carboxylic acids by reacting it with a carbonate. So the practical setup looks a little bit like this. So we have our carboxylic acid in here, so whatever that is, and then we can use carbonates in here. We add a carbonate in here. If a carboxylic acid is present, then we get carbon dioxide gas is produced, and to test for that gas we bubble that through lime water, and it turns lime water cloudy if there is indeed a carboxylic acid present. So a suitable carbonate to use would be something like sodium carbonate, solid sodium carbonate, or we can even use sodium carbonate solution. It's probably better using the solid version. We've got to be really careful though with this one, caveat this quite a lot. Any other acid will react in the same way. It's not a definitive answer to say that you've definitely produced a carboxylic acid. You're going to have to do other tests or analysis to do that, such as NMR, infrared, etc. And the final type of functional group test, as we've seen before, is alcohols, or test for alcohols. This is quite an important one actually, because we need to be able to identify if an alcohol is primary or secondary or tertiary. So acidified potassium dichromate is used, as we've seen before. We can distinguish between these alcohols. Now, acidified potassium dichromate, remember, oxidizes primary and secondary alcohols, but it won't do that for tertiary alcohols. So we're just using this method, but we're actually flipping it on its head, and we're going to use this method as a test rather than as a functional reaction to produce a certain product. So primary and secondary alcohols, these are oxidized using acidified potassium dichromate solution. It's a mild oxidizing agent, and remember, it's been reduced itself, so it'll go from orange to green. Okay, if indeed you do have a primary or secondary alcohol. Tertiary alcohols, they won't do anything. So if you add tertiary alcohol to potassium dichromate, you won't get a color change. So that in itself distinguishes between primary and secondaries and tertiary alcohols. So the problem lies though with primary and secondary alcohols, because they both give the same colour change. So how on earth are we supposed to distinguish between the two? Well, remember what we said before is we can use fractional distillation. There's the setup shown on the right there, and we collect the products produced upon oxidation. So we take our chemical, okay, and we separate it out. Basically, we use distillation. There we are. And if we have a primary alcohol, then what we should see is an aldehyde being collected in here if we are actually indeed heating up a primary alcohol. If not, if we end up with a ketone in here, and obviously we can test that using toluenes or phthalings or any one of these chemicals that we're producing, then a ketone will not oxidize any of them. You'll get no color change. So effectively we're doing it in kind of a long-winded way, but that's how we can distinguish between primary, secondary, and tertiary alcohols between all of them. Okay, and that's it. That's everything you need to know for organic reactions, carbonyl compounds, and functional groups for the Colour by Design topic, the CD topic. Like I say, there is a full range. This is one of 3 videos for the CD topic, but there is also a full range of revision videos like this for Year 1 and Year 2 OCRB Salters course. There's also some whiteboard tutorials, generic whiteboard tutorials as well. They're all for free. All I ask is you hit the subscribe button. That'd be absolutely fantastic. And then also, if you'd like a copy of these, they're great for revision. Print them out, put them in your file. Then you can click on the link below and you get the full range there. Great value for money. Right, that's it. Bye-bye.